Hello, everybody. I'm Levente Tsumbil from the Technical University of Cluj-Napoca, and in the following, I will present some of our works regarding evaluation of electromagnetic interferences affecting metallic pipelines. From some years, we studied the effect of electromagnetic interferences produced by high voltage power lines on nearby metallic object. And here we have a close collaboration also with Theophilos Papadopoulos. I think he is on site in the room. Regarding how we can evaluate the induced voltages and currents in such kind of metallic structures that are nearby high voltage power lines. Why are we interested in such phenomena? Is due to the fact that the induced voltages and currents could affect nearby metallic structure from 2 points of view. First point of view is the hazard of electrocution of personnel, of people who can come in contact with this kind of metallic structures. If we speak about pipelines, then this could be the personnel who operate the pipeline, or if these pipelines are above ground pipelines, then anybody who can come in contact with these metallic pipelines could be affected by electrocution if they touch the pipeline, and of course if such kind of induced voltages appear. The second point of view is the structural the structure of the pipeline. Due the induced voltages and especially due the induced currents, if the pipeline is an underground pipeline and it's buried in the soil, then the induced currents that are leaving the pipeline also produces a movement of electrons, and this movement of electrons, it means that we have a movement of material from the pipe to the surrounding soil, where at the place where the current leaves the pipe, and so we could have corrosion and could the integrity of the pipe. And unfortunately, in the 80s, it was such kind of event in Arabia when one pipeline exploded due to heavy corrosion next to due to the effect of the induced currents and voltages. So this is the problem that we study. We studied the effects of induced electromagnetic interferences in nearby metallic structures due to high voltage power lines, due to the electric and magnetic field produced by such kind of high voltage power lines. The standards and regulations impose some limits with regard with the maximum level of the induced voltage levels that could or are allowed to appear in such kind of metallic structures. We have here some imposed values with regard to the time duration of the effect of the fault. From a point of view of safetiness of the person who could come in contact with the metallic structure. From a point of view of corrosion, the induced voltage level should not exceed 1.2 volts. So from a corrosion point of view, these limits are more drastic. And in order to protect this kind of pipelines, usually the operating system, the operating person of the pipeline use to maintain the pipe all the time at a negative potential level in order to avoid the movement from the pipe to the surrounding soil and to have corrosion. Okay, but set the catalytic protection, you have to know the level of the induced voltages that could appear in the pipeline. So let's look what are the phenomena that could produce such kind of induced voltages and currents. Actually, there are three kinds of coupling, of electromagnetic couplings. The first one, which is the most common, is the inductive coupling, which is due to the magnetic field produced by the power line. As we know, any structure which is through which we have a current flow produces a magnetic field surrounded, and if this magnetic field is time varying, this field will induce an electromagnetic force, an induced voltage in any nearby metallic structure. So this inductive coupling we have in all cases around high voltage power lines, even if the pipeline which we are studying in our work are above or underground. The second coupling, one question, do you see my mouse?
Yeah.
Okay, good. The second coupling, the capacitive coupling, is due to the electric field. And this kind of couplings we have in our case only in the case of above ground metallic structures, because at low frequencies the earth works as a perfect conductor, so actually insulates the electric field, the pipe, from the electric field produced by the high voltage power line. The third coupling is the conductive coupling, and this could happen when we have a direct connection between the two systems, galvanic connection. If, for example, the pipe is connected to the grounding system of the power line towers, or if the two systems, the grounding system of the power line towers and the metallic pipeline, are very close to each other, and in case of lightning strikes, lightning faults, when we have a huge current, lightning current that flows to the towers to the ground, this huge lightning current could produce ionization of the soil surrounding the grounding system, and to have a lightning current leakage towards the pipeline. But this conductive coupling could happen only in this kind of lightning faults, or let's say if we have a face to ground fault when one of the phase wires due to a storm is broken and falls to the ground and it's close to the pipeline. Okay, in the following I will discuss about how can we model these phenomena in order to evaluate the induced voltage, and I will use a case study between an ideal 400 kV power line and the gas distribution metallic pipeline, which I consider to be placed under the ground at 1.2 meters depth, at a separation distance of 50 meters from the high voltage power line. In order to compute the coupling phenomena between the power line and the pipeline in EMTP-RV, we have to look to the current distribution corridor as a single transmission line to model the whole power line and the metallic pipeline transmission line. And starting from EMTP 4.2 comes the good news that the guys from EMTP implemented the so-called line cable data model, which allows to model in the same transmission line element above ground systems, above ground conductors, and underground cables. This is the good. It's much easier to study and to model this kind of situation. Before, we had to make a consideration that everything are cable and force a little bit the model, saying that the above ground power lines, conductors, phase wires, and sky ground wires are actually some cables with air insulation, but which are placed at a depth which is above ground. But as I said, with this new transmission line model, line cable data model, it's much easier, and we actually can model what we have in place in this kind of complex combined above ground with underground conductor. So in order to model our problem with the line cable model, combined line cable model, yes. I heard something Was it a question?
No, continue.
Can I continue?
Yes, please.
Okay. For the beginning, we consider only the phase wires of the power line because these are the most important conductors that produce electric and magnetic fields. We consider our phase wires. We present here the data introduced for a classical 400 kV power line. And in order to model the nearby pipeline, we consider it a pipeline metallic structure. We consider that the conductor of the cable tube type cable with a radius. The insulation of the pipeline, which is meant to protect the metal of the pipe from the surrounding soil and from the chemical corrosion in the soil, we consider as the electric insulation of this equivalent cable. And we have here in the slide the data of 0.4 yes, now I see that. Okay, we had a little bit of mistake in the data. We were used to the previous version with radius in meters. Okay, it should be 0.4 meters, not centimeters, the radius of the pipeline. And also we have in this combined line cable model the possibility to provide the soil resistivity. We worked with a general 100 ohm meters, but the model allows us also to introduce multi-layer, horizontally layered soil structures, which can be obtained from on-site soil resistivity measurements. In order to compute the induced voltages and currents in the metallic pipeline, we have to create a wideband transmission line model, which allows us not only to study the electromagnetic interference problem in steady state at a working frequency, usually in Europe 50 Hertz, but also allows us to study transient phenomena as similar to lightning effects. And as at the beginning of this conference, the line cable data model is under construction, under testing, and this moment for this kind of coupling phenomena in the 4.2 version of EMTP-RV, only this wideband transmission line model was properly working. The frequency dependent and the constant parameters models had a little bit of problem with the right evaluation of the coupling and of the induced voltages and currents were not properly evaluated. We tested together with Theophilos. We were working last year on this. So we have here an example how this wideband model should be set up in EMTP-RV in order to have a proper evaluation of the induced voltages and currents in the metallic pipeline. Using the wideband mathematical model created by the combined cable data model, we could construct the equivalent circuit of the that we studied. Here we have an implementation with a single transmission line wideband model, having on the left model the grid, the voltage source, and on the right the load, the current load as a power load of the high voltage power line. And in order to evaluate the induced current and voltages in the metallic pipeline, we put some current and voltage meters. And also in our first simulation, we consider that this section, this common right-of-way section, is insulated from the point of view of the metallic pipeline, is insulated from the ground and is insulated from the rest of the pipeline network, considering an ideal insulation with a very huge resistance. We made the EMT simulation considering the 400 kV power. We have here the load on the three phases of the power line and the load current in each of the three. For this power load, we evaluated the induced voltage at the pipe ends and the induced current, actually the current to the ground at the end of the pipelines. If we look at the induced voltage, we can see that as expected, it's a sine wave due to the fact that the power line is loaded with sine wave alternative current, AC current, and it's quite huge, is about 13 volts value, which is quite huge from a point of view of corrosion. Okay, this kind of modeling with a single transmission line element allows us to see the maximum induced voltage which appear at the end of the power line of the pipeline section that we study, and do not allow us to see what happens along the common. In order to see the influence of the grounding of the pipeline, we made a second considering that of the common right of way, the pipeline is connected to 20 ohm resistance grounding, and we evaluated the induced voltages and current. What we can see, if the pipeline is grounded, of the pipeline, the induced voltage values decreases quite a lot, and it's almost at the level of the at which we can say that no corrosion will happen. So this kind of connection of the pipeline to the ground could be used as a measure to protect the pipeline from induced voltages and to limit the induced voltage values. But the backbone of this connection to the ground is the fact that the current that flows to the ground at that place will increase. Therefore, also this kind of connection to a resistance could be used to simulate and model insulation defects on the pipeline, and to see what happens if, let's say, the pipeline is not perfect due exploitation in time appear, let's say, holes in the insulation, what will be the current that will leave that insulation fault, and how this could place. In order to present the most important parameters that affect induced voltages and currents in metallic pipelines that are next to high voltage power lines, we consider a reference case with a not so ideal insulation of the pipeline, considering a more realistic and more the resistance of the insulation coating, considering a 20 kilo ohm resistance for our system. If we compute and model a first case when we have insulation at one end and connection to the ground of the pipeline at the at the other end, we could see that at the end, which is insulated from the ground and from the rest of the pipeline system, we will have an increase of the induced potential. And of course, at the end, which is grounded, the induced voltage decreases. At the level of the currents that flow from the pipeline to the ground, this is reversed. At the end where the pipeline is grounded, we have a higher value of current flowing to the ground, and at the end, which is insulated as expected, the current is smaller. As I told you before, if you consider this 20 kilo ohm value for the insulation at the both ends, and we make the simulation, we could see that the induced voltage values are similar, almost identical to what we get for the first case when we consider that ideal insulation resistance value, and the currents that are flowing to the ground are directly proportional with the value of the resistance. Okay, but this approach, when we model the entire common distribution corridor as a single transmission line element, allows us only to see the maximum value of the induced voltages, which appear at the end of the pipeline, at the ends of the pipeline. If you want to have a more detailed information, what happens along the distribution corridor and how the induced voltage varies along the pipeline, we have to divide the common distribution corridor in multiple subsections, and usually this division is made considering the length between two power line towers. So in our case, we divided the 5-kilometer common distribution corridor in 10 subsections, each of them 500 meters. Let's say the longest distance between two power line towers at a 400 kV voltage level. This division of the common corridor in multiple subsections and placing measurement units at the end of each section allows us to evaluate the induced voltage and currents at multiple points along the pipeline length. As we can see, the induced voltage is not the same along the pipeline. We have maximum RMS values at pipeline ends, and the induced voltage value decreases towards the middle of the pipeline, length. And also, if we look to the voltage sine waves on the pipeline, we can see that at the both ends, the voltage is opposite as value and sign. With regard to what happens to the current, the leakage current that flows from the pipeline towards the ground, it's the phenomena, it's opposite. We have smaller currents flowing towards the ground at the end and higher current values at the middle of the pipeline. Here we can see the variation of the induced voltage as RMS value along pipeline length, and us who worked with this kind of electromagnetic interference problems could recognize the V form of the induced voltage along the pipeline length, with maximum values at the end of the pipeline. And as I said, if we look to the induced current values, this is quite the opposite, minimum values at the end of the pipeline section and maximum values in the middle of the common distribution corridor. Okay, but this simulation was made ignoring, neglecting the sky wires and their effect on the interference phenomena. In the next, we introduced in the transmission line model also the sky wires, ground wires. In our case, for the 400 kV power line with horizontal distribution of the phase wires, we have two sky wires, ground wires, which are placed at 35 meters height. We have the equivalent wideband transmission line model that we created, and we replaced in our EMTP circuit model each section with the new wideband transmission line model, considering the presence of the sky wires. For our first evaluation of the induced voltages and currents, we considered, let's say, an ideal case when the sky wires are interconnected from one end to the other, and they are grounded only at the end of the common distribution corridor. Let's say in this case, we ignore the presence of the towers and the metallic connection between the sky ground wires and the metallic structures of the power line towers. Using the EMTP-RV, we simulated and firstly present you the induced voltage and currents in the sky wires. They are also metallic structures, so do the electromagnetic field created by the power line phase conductors. In this case, we have both inductive coupling and capacitive coupling. The sky wires are above ground, so they are not protected from the electric field to the surface of the earth. We have induced voltages and currents. These currents that are flowing through the sky wires, they produce also electric and magnetic fields, so they have an effect on the metallic structure of the pipeline. Here we have the evaluation of the induced voltages and currents on the metallic pipeline, considering the presence of the sky wires. If we look to the RMS values, we can see that if we compute and if we consider in our modeling the presence of sky wires, we have a difference at the end of the pipeline where we have the maximum values of induced voltages of 5%. Consider the presence of sky wires. Induced voltage decreases. Why? Because the current that are induced in the sky wires have current that are flowing to the phase wires. So actually the magnetic field produced by the sky wires will reduce the effects of the coupling between the phase wires of the power line and the metallic structures of the pipeline. But one problem with this circuit is the fact that it's not what we have in place in reality. In reality, at each power line tower, the skywire ground wires are connected to the metal of the tower and connected to the ground. So a proper modeling, it will be to consider also the presence of the tower and the connection of the sky wires at each tower and the small loops that are formed between two towers. We have here the, let's say, more realistic representation of the common distribution corridor, considering the presence of skywires and considering the presence of the tower. In this moment, consider the tower to a grounding resistance of the skywires. Using this new, more complete EMTP-RV circuit model, we could compute the voltage at the tower tops, considering the induced current in the skywires. We could see that we have a maximum of 3.2 volts, which is much lower than what we had in the first case when we considered the skywires connected to the ground only at the end. And also we can see that between each two towers, we have a circulating current through the loop formed by the skywires. Okay, we evaluated the induced voltages and currents in the metallic pipeline, which is our interest. If we compare to the previous results, we can see that from a point of view of the induced voltage values in the pipeline, this more proper simulation has not such a big influence. So if you are interested only what happens in steady state on the pipeline, we could neglect the presence of the towers, and if we are not so interested in a very accurate evaluation, also the presence of skywires could be neglected for steady state simulations. In the following, I will discuss and I will present some of the parameters that affect mostly the level of induced voltages in the pipeline. And these are, first, the separation distance, how close it is the pipeline to the phase wires of the power line. We consider different separation distances from 1 kilometer to 20 meters. And we can see how the induced voltage varies considering the maximum induced voltage values that we obtain at the end of the pipeline section, and we can see that as the pipeline is farther away from the power line, the induced voltages decreases. Here we have a small difference between the value of what happens if the pipeline is on the left or on the right side of the power line. This is due to the physical position of the phase wires and the geometry of the power line. As I said, in our case, we simulated a horizontal distribution of the phase wires on the power line. Another important parameter is the soil resistivity. In steady state conditions, if we increases the soil resistivity, we will have a, let's say, logarithmic increase of the induced voltage values, but the value of the soil resistivity has a bigger impact in case of conductive couplings, in case of lightning faults, and if the pipe is close to the power line and soil ionization could happen to break down the resistance of the ground due to the high lightning fault current. And in that case, let's say it's better to have a more resistive soil. On the other hand, if we look to the protection, the value of the soil resistivity has a huge impact also in the proper setup of the cathodic protection system. Of course, the length of the right way has a huge influence. We have a representation how the induced voltages increases considering the length of the common right way. And of course, the load, the current load of the power line. In order to study the induced voltages and currents in the metallic pipeline due to the variation of the load, of the current load on the power line, in steady state, we can make a switch to more easily simulate the power line, and instead of considering a power load, we can put a current source which will force the current flowing to the power line phase wires. But be attentive, this kind of replacement can be done only if you want to study what happens with the pipeline, with the induced voltages and currents in steady state conditions. If you want to look to transient phenomena, we have to work with the initial power load element. So I have here presented the obtained results, how the induced voltages varies for our investigated power line with the load current, considering an usual range for 400 kV power lines. So this will be the main parameters that influence induced voltages in pipelines that are placed next to high voltage power lines, and the way how the common distribution corridor could be modeled using EMTP-RV. What I have to also mention that in the simulations presented by me, I considered an ideal case of parallel exposure when the separation distance does not vary along the common distribution corridor. Okay, this do not happen in reality. In reality, if you want to model a real case, we have to evaluate the equivalent separation distance for each section of the common distribution corridor, considering, as I said, in first place as a section length, the distance between two power line towers, but in case of real oblique exposures, when the pipeline is not parallel to the power line, also we have to look that the distance at the ends of the section that we consider and we want to replace with an equivalent parallel section, the ratio between these distances, it's not higher than 3. If the distance ratio is higher than 3, then the in sub and multiple subsection to respect also the ends of a section, the distance ratio do not be higher than 3. If you have a case when the pipeline intersects the power line, undercrosses the power line, then a section where the distance varies from plus 10 meters to minus 10 meters, in the modeling, it is usual to use an equivalent separation distance of 6 meters for the entire section where the pipeline undercrosses the power line. So this would be some recommendation how to electromagnetic interferences. So if you have any questions, I'm here to answer you.